Howdy. All right, so it turns out that on open intervals, local and global maxes for functions that are mostly differentiable occur for one of two reasons. And if you draw a picture, you can see sort of what's going on pretty easily. So if this is your function f, you can see you've got a global max and a local max and a local min there. And at each point, of course, the tangent line will be horizontal. It's flat, which means the slope of the tangent line is 0. So local max and local mins can occur when the derivative is 0 at those points. But there's a sneaky one as well, where you can get a local max occurring, and that can be a place where the derivative doesn't exist. So if you have a function that looks like this, then you've got here another global minimum, in fact, and this point isn't where the derivative is 0. In fact, it's the place where the derivative does not exist. And it turns out that, as I said, in these scenarios, those are the only two places where you might have a local max or a local min. So we give these types of points special names. They're called critical points. So a critical point for f happens when either the derivative is 0, a critical point c happens when the derivative is 0, or the derivative at c does not exist. Okay? Now, the way you should think of these critical points is all the potential candidates for where a local max or local min might be. So here is the theorem. If C is a local max or min, then it is a critical point. Okay? Now, the way you should think of these, therefore, is the critical points are a list of places where f might have a local max or a local min. I want to emphasize the word might, and the reason I emphasize the word might is because there are pictures like this of functions like x cubed that look like this, and here the derivative is 0, so that it is a critical point, but it's not a local max or a local min. Okay? So being critical doesn't guarantee that you're a local max or a local min, but it is a list of all the places local maxes and local mins might occur. And we'll tell you shortly how to tell the difference. But for now, let's just do a couple of examples where we find some critical points. So the first example is this. Find the critical points for this function. F of x equals x cubed minus 9x squared plus 24 minus 10. All right? So critical points happen either where the derivative is 0 or it's not defined. Now this is a polynomial. It's infinitely differentiable. The derivative always exists, so the only possibility is to find out where the derivative is 0. So first, you have to find the derivative. So we do that. 3x squared minus 18x. Did I forget an x there? I did. Plus 24. All right. Now we see each of those terms. We can factor 3 out, so let's do that. It's left with a x squared minus a 6x plus an 8. All right. And we want to solve where that's 0, so anticipating that, let's factor it. We get a 4 and a 2, so x minus 2 and an x minus 4 is how it factors. So the next step is to solve this equation, f prime of x equals to 0. So that means we have to solve 0 equals to 3, x minus 2, x minus 4. And so the only solutions are x is equal to 2 and x equals to 4, and these will be the critical points. All right? Let's try one more example. Let's do f of x equals the absolute value of x. All right, this one you can do with a picture. Remember the absolute value of x looks like this. 45 here, 45 degree there. You notice nowhere is this curve flattening out, so the derivative is never 0. But you do see this one place where the derivative doesn't exist. So f prime does not exist here. So the only critical point is where x is 0, where the derivative doesn't exist. All right, that's it for finding critical points. See ya.